some fantastic identities and where to find them.
So thank you very much, Terence, for inviting me to speak in the seminar. Let me just start off by doing a little bit of talking before I actually start writing stuff on the board. My one class a day that I just got done teaching was an exam, so I haven't got to talk much today to people, so I'll take advantage of that right now. So let me just kind of sketch out how this is going to go. There's going to be kind of maybe four segments to the talk. The first one is just going to go through partition basics and what partition identities are. So if you've seen that before, bear with me, although there probably will be at least one new identity in there that you haven't seen before. And then it'll be good for those of you who are new to partitions. And then the rest of the talk will kind of be three separate, time permitting, not sure how much I'll be able to get through, but time permitting, I'll have kind of three separate research projects I worked on with various groups of people. And so the big takeaways I want you to get from this, especially for those, so first off, for those of you new to haven't seen me talk about partition before, have a sense of just, let me emphasize that fantastic word, but there are some really cool, in my opinion, identities that come out of the realm of partitions. For those of you who have seen me talk about stuff before, let me emphasize this word where. Because many of the techniques, so there will be some new techniques that I'll be using, that kind of differentiates this from previous talks that I've given, but some of the techniques will be old. But one of the more important things is knowing where to look for them. So my friend and collaborator, Shashank Kanade, we actually had a brief discussion after I agreed to give this talk about what to call this. And obviously, where is the name from the books and the movies kind of thing. I initially thought, oh, maybe it should be how instead. But no, we ended up like where. Knowing where to look for these is a very important thing. So pay attention to that. Also, let me just say that if there's ever stuff that isn't making sense, please raise your hand. Please ask me questions. I'd rather have people understand what's going on and not get through everything I have prepared than get through everything I have prepared and have people not understand what's going on. So, okay, this is the part where I will get Nathan to chuckle a little bit when I define what a partition is. I'll just kind of do definition by example here. What are partitions? So pick a positive integer like 6. Let's just list out all the ways that we can write 6 as the sum of other positive integers where we don't care about order. So there are going to be, let's see here, I think it's 11 partitions of 6. So there's 6 of them. Here comes 3 plus 1 plus 1 plus 1. 2 plus 2 plus 2, 2 plus 2 plus 1 plus 1, 2 plus 1 plus 1 plus 1 plus 1, and then the last one is always going to be 1, 2, 3, 4, 5, 6 ones. Let me just observe here, our tradition is we always write the parts in non-increasing order. We're going to have them go down here, and so the point is we don't care about order. So you say 2 plus 4, well I say I've already got 4 plus 2 in the list, that's taken care of. So one question we can ask, for a given n, how many partitions of n are there? That's a fine question to ask.
41?
What's that?
So I guess 41.
Sounds about right, yes. We can also, instead of just looking at partitions and counting them, we can also look at various restrictions. So for example, instead of just looking at all partitions, we can say you're only allowed to use odd numbers when you're doing it. So 5 plus 1 would be okay, 4 plus 2 would not be okay. So let's see, now I'm giving talks and I feel that now I have a PhD, I'm allowed to call on people. So Nathan, how many partitions are there that only of 6 that only use odd parts?
I see 4 of them.
Let's see, 1, 2, 3, 4. Yeah, that looks
Be
good.
advised, if you're calling on me, I'm also paying attention to recording.
Yeah,
your talk,
so we are going to see how challenging we can make this for you. So that's one thing that we can use, just like, say you're only allowed to use certain types of integers. In this case, we're doing only odd numbers. Perhaps it's pick some set, like only numbers that are congruent to 0, 3, 5, 6, 7, mod 9. You know, something like that. It's perfectly allowable. Another thing that we can do is say that you're only allowed to use, you're not allowed to repeat any parts here. So for example, 5 plus 1 is okay. 4 plus 1 plus 1 is not okay because the 1 is repeated. So Justin, how many partitions are there that are distinct here?
It's looking like 3, 4.
Yeah, so this 1, 2, 3, and 4 looks like that. And so we also have 4, and then we have a conjecture. 4 is equal to 4. How about that? And due to Euler, we have this wonderful theorem that says, you know, I usually just say Euler odd is equal to distinct. So for any positive integer n, the number of partitions of n that only use odds parts is the number of ones that don't repeat at all. And so this is our first example of what I'll call a partition identity. So this talk, partition identities and where to find them. This is our first partition identity. Number of partitions in one type equals number of partitions into a different type. And so kind of the rest of this talk is going to be looking for various identities and stuff like that. Any questions so far? So let me, before getting into the rest of that talk, let me just kind of set up some machinery. And I'll be looking most particularly at, for right now, this machinery for the stuff that looks like this. When I said odd numbers kind of thing here. And so this is going to be what I'm going to call the product side. Now, it's time to talk about generating functions. I'm going to kind of briefly go over this. First, let me write down the generating function for, so I'm here, I'm using Q as my dummy variable. This is the generating function for partitions with no restrictions whatsoever on them. And then if I were to want to only allow myself to have certain numbers, let me just kind of say something. You know, I can just say j is at least 1 and j falls into some set here. You know, so that set S might be the set of all odd numbers. It might be the set of all numbers congruent to 1 or 4 mod 5. Whatever it is, that's what I have. Let's see. What else can I do with here? I'm going to kind of say that let's move away from this a little bit. Let's just assume that you give me some formal power series. Any formals, I can take a formal power series. And any formal power series you give me, I can write it in this form. So the product of over all j greater at least 1 of 1 minus q to the j raised to the aj. So I'm going, you know, those are some exponents there that they could be, you know, in this case they're all going to be equal minus 1 because I'm dividing by 1 minus q to the j. They could be 0 stop appearing. In certain cases I might let them be minus 2 or plus 1 or stuff like that. Those will all be okay here. But the point is that this I can do this uniquely. Assuming that I have a form of power series, and I think I also need to say something that the constant term is 1. You know, for my purposes.
The coefficients
Coefficients have, yeah, so the coefficients have to be integers, all of mine are going to be positive integers, non-negative integers. So I'm sweeping some stuff under the rug here, but everything I'm saying is going to be working for the stuff that I'm caring about. And so if I have, so for any, if you hand me a formal power series, I can turn this into this kind of object, and I can just say, okay, what's the A sub j sequence? And I think the OAIS people like to call this the Euler transform. Yeah. So Euler transform is going from your formal power series to the sequence of A sub j. And so our goal L, and colon there, find periodic AJ sequences. So, for example here, odd, my periodic sequence would just be, I'm starting in, -1, and all the odd ones are raised to the -1 power, all the evens are raised to the 0, and just iterate that forever. So now that I have that, a little bit of background, let's start talking about some more identities questions.
So you can start with the period and compute to the system.
Yeah, so certainly, and very good point. If we have a periodic sequence, we could certainly compute as many terms of this as we want. That's actually something I'll be doing at the end of the talk. Kind of, you've seen me talk before, kind of reverse the way that we usually think about this. Okay, so after Euler, we have to start off with Euler, but my next one is going to be, you're going to like this, your mathematical hero, Major McMahon. And so, again, you see me talk before, this is one you probably haven't seen before. McMahon's identity is going to be, to the product side, the thing that looks like odd numbers or stuff like that, let me just write this as the sequence here is 0, -1, -1, -1, 0, -1. So this is into parts that are congruent to 2, 3, 4, and 6 mod 6. And then the sum side, the stuff that kind of looks like these difference conditions, is going to be, have the following two things. The first is that you're not allowed to have both j and j plus 1 in your partition. So if you have a 5 in your partition, you can't have a 6, you can't have a 4. But, and there also is an initial condition here. The initial condition is that you're not allowed to have any 1s whatsoever. That is our initial condition.
It's because you have zeros.
Right, and so in some sense, one kind of thing that over the past year, I've been learning a lot about this kind of thing. And one thing that I've grown to appreciate is that a lot of these identities, they have what Shashank and I have been calling fictitious zeros here. So in a sense, our partition, is going to have some 0 in it. It doesn't actually appear, it's not really there, but having that 0 means that we can't have a 1 in it, because we're not allowed to have consecutive 1s. I don't know if it's fair for me, this is a more open-ended question, I don't know if it's fair for me to ask this in a similar. Anybody knows anything that's not here, that like most of the identities I've talked about in the past, they have some condition that's not appearing here? So, yeah,
Some sort of congruence condition on the
some
side.
sort of congruence condition, sure. We'll eventually work that in here, so that's not a bad guess, and that certainly is true. I think this is kind of an unfair question, so I answer it myself. One difference here from previous identities that I've discussed in previous talks here is that you're allowed to repeat parts as many times as you want. So stuff like on the quote-unquote sum side. So when I talk about Rogers Ramanujan, you have this difference 2 condition. So I say if you have there's a kind of difference 2 condition here, but you can also repeat parts, and that's a key difference to what I've done before. So this is a new place to look. Let me just go back to this, where to find them. This suggests that we have a new place to look. Any questions about McMahon? So at this point of the talk, I'm going to kind of start talking about.
Can you spell out the product side?
Can I spell out the product size? Sure. So the way I'm kind of writing this is 2, 3, 4, and 6. So this is parts congruent to 2, 3, 4, and 6 mod 6.
Not equal 0.
For some reason over the past year or so, this feels more natural than to say 0, 2, 3, 4. I think it's because the first 0 doesn't appear in my partitions. I have no it's personal taste.
Maybe because Maple Index is from 1.
Maybe because Maple Index is from 1. Take your pick of explanation. I don't have a good reason
So this
for
is
it.
not sure, because sure also is something with mod 6.
So you're right. Shore is something to do with mod 6. Shore is actually the missing ones here. The shore product side is 1 of 5 mod 6. I remember, this is dangerous to say on camera, but I remember Shashank and I were talking and trying to fill in the, is there anything you can do that Shore and McMahon fill in each other's gaps? Can we say anything interesting about that? I don't think we came up with anything, but it is an interesting thing to think about. Okay, so in terms of where to look, so now we kind of have an idea of where to look, and let's kind of discuss how to look for them in terms of computer experimentation. And so the point of this project, and
So
then
any partition is a sum, uniquely a sum of 2 partitions.
right,
One of the McMahon type and one of the Shore type.
right, and so something to think about. I don't want this is. Up in front of people on camera, I don't want to make any, say anything too strong here. Okay, so experimentation, the goal, as you guys may have guessed, is let's find new identities. Let's conjecture them. If we're feeling lucky and feeling adventurous, we might even try to prove them, kind of thing. But this new kind of this new to us, Shashank and I also, so Deb Nandi, another recent Rutgers PhD graduate, now back in India, he's also working on this project. So experimentation is that let's go ahead and say we're banning certain difference. So in McMahon, we're saying you can't have difference exactly equal to 1. You can have difference 0 between parts, you can have difference 2, 3, 4, 5, 6, whatever you want between parts, but you can't have difference exactly 1. So this is one thing to think about. And then I'll kind of refine this, tack on a couple more things here, like, okay, this has been done before, so what's kind of our contribution here? How should we think about anything's exactly right? Let's kind of think about, include congruence conditions. For instance, so like we might say, even parts get treated differently than odd parts. That some difference conditions might only apply to even parts and not to odd parts, or vice versa. That's something to think about. And then when we, after we've come up with a big list of difference conditions, for each kind of possible combination of difference, come up with lots of them, throw in some initial conditions, as you observe, maybe oftentimes coming from a quote-unquote fictitious zero here. And then we can calculate out lots of sum sides. And so this is something that we can do in Maple. Just ask Maple, tell us all of the partitions of 1, 2, 3, 4, 5, all the way up to 30, 40, 50, however far we want to go when we have computer time. And just brute force this, for each partition, ask, does it satisfy whatever difference conditions you're looking at a time? And okay, now you have some powers, the first, 30, 40, 50 terms of some power series. And once we have the first, so many terms of the power series, we can check the product side. There's the, we can use the Euler transform to look at this sequence here, and if we get something that looks, okay, we probably aren't going to get this again, unless, but if we get something very nice and periodic that hopefully just -1, zeros, some +1s are okay in there. There's certain ways that we can handle that those aren't terrible. -2s will also be acceptable in some cases, maybe. And so if we do that till we find it, then hey, conjecture. So any question about this kind of experimentation process?
You could look them up.
So looking them up in the OAIS probably should be included as a step in there to make sure that if we get a positive, that look, here's a conjecture. Has anybody noticed this before? So yes, that is certainly, and I probably didn't want to erase those partitions, but oh well, you can always now comes the results. The fantastic, so we were discussing where to define them. Now let's do the fantastic identities part of it. So here are, I'm only going to do a small kind of sampling. Like we have tons, we have a paper that's about 20 pages long just of conjecture after conjecture after conjecture. Some of them, there's obviously exposition and stuff like that in there, and they're all in these families and stuff like that. But I'll just kind of present a couple of them, so that are hopefully illustrative.
And their own conjectures still.
I'll be discussing that at appropriate parts. So, okay, so here is one where there's the Euler transform, so I guess that is 1, 2, 4, and 6, mod 6. Yep. Is the product side. And the sum side is you can't have both 2j and 2j minus 1 or 2j and 2j minus 4. So
your product side is just a cyclic shift.
Product side is just a cyclic shift.
That doesn't help?
So that's a very good point here. That is something that we've certainly looked at in terms of what can we do here. I don't think, again, there has been. I'll come back to that kind of discussion later on. Talk I think is will be more appropriate.
So since you have so many minuses coming up, might be better to write minus AJs.
Sure.
That's
sure.
right.
But that's the OAIS convention. Don't want to.
Occasionally,
Yeah. Okay. It's a convention. We can deal with it. Let's just kind of note here. So in terms of like our banning certain differences. So this basically says, you can't have a difference 1 backwards from an even part. You can't have a difference 3 backwards from an even part. That's what's going on here.
Wait, so you can't have either of those? You can't have both of them?
Okay, you can't have either of those. So you can't have this. Also, you can't have this. that is the order easier to do verbally than writing on a chalkboard. Inflection can get a lot across. And I'll just say there's a whole infinite family of those that here's a kind of small example, but there's one if you can't go 1, 3, or 5 backwards, 1, 3, 5, or 7 backwards. Whole family of those. Let's see here. The next one, the product here, -1, 0.
I'm sorry, when you're calling them results, these are conjectures or they're...
Yeah. So I think again, let me come back to that later on in the talk. Yeah.
But at the moment, there are everything we should think is conjecture, experimental.
Sure.
Okay. Yeah. At some point, you tell us which things.
At some point, I will kind of elaborate on proofs and stuff like that here. Part of that is that the answer there it is not the same for all of these. I want to make sure I accurately say which one is which. So here is a product side mod 12. So I guess this is 1, 4, 6, 7, 8, 10, and 12, mod 12. The sum here is that the first rule is odds can't repeat. And the second one is if 2j plus 1 is present, so if you do have an odd part, then there's a bunch of other parts you can't have either. Tell you which ones those are as soon as I erase. So if you do have an odd part, 2j plus 1 can't have any 2j plus 2, 2j plus 3, 2j plus 4, or 2j plus 5. And once again, this is an infinite family. I'm sure you can see how to generalize, generalize that sum side. So now you just go 2j plus 2 through 2j plus 7, and through 2j plus 9, and stuff like that. And so that is another one.
Okay, so the first one was if 2j is present, then cannot have 2j minus 1 and comma 2j minus 3.
Yep.
Okay, that would be a simple way of writing.
Yes. Yeah, this is all, this is my first time, talking about this in public. It's one of those things like I haven't quite worked out. It makes sense in my mind, haven't quite worked out what is the best way to do the expedition on this other people. So thanks for your feedback. So one more here. Product. So 0, 0, minus 1, 0, minus 1, minus 1. Minus 1, 0, minus 1. This is a mod 9, so I think this was the one I said before. So 3, 5, 6, 7, and 9 mod 9. And the sum is going to be a little different than the others. So you can't have difference 1. You can't have both j and j plus 1. If the difference between adjacent parts is equal to 2,